Welcome back to the next video, everybody. Today, we're going to go through an example looking at the Selmer groups we covered last video. So let's let P be an odd prime. Let's let X be Z mod P to the NZ with the trivial Galois action. We'll let S be a finite set of primes containing P and the infinite prime. For L and S, let's let big L sub little l be H1 of G sub L Z mod P to the NZ. For L not an S, let's let big L sub little l be H1 of GL mod IL Z mod P to the NZ. Okay, then L perp sub little l is 0. It's trivial for L and S. And L perp sub little l is H1 of GL mod IL mu sub P to the N for L not an S by theorem 1 from a previous video. If you were to look into the proof of the main result from the previous video, you would see that every element of H1 of GQ mu sub P to the N is represented by a cocycle of the form G maps to G alpha over alpha, where alpha to the P to the N is, which we'll call A, is in Q cross or Q star if you like. Now, to live in H1 sub cal L star, this element must be unramified everywhere, just based on the setup we have up here. By a fact from a previous video, H1 of I sub L mu sub P to the N, which is H sub 1 of G sub Q NR L mu sub P to the N, that's isomorphic to Q NR sub L cross mod P to the nth powers there. Okay, so we talked about this several videos ago. And so for an element to be in H1 cal L star, it would have to be unramified everywhere. But based on this description of H1 I sub L mu sub P to the N, for that to happen, it would have to be the case that the L-adic valuation of alpha was 0 mod P to the N for all L. In other words, it would have to be the case that A is a P to the nth power in Q, and the cocycle then will just represent the trivial cohomology class. And the upshot of all this is that H1 of cal L star Q mu sub P to the N is 0. It's trivial. Let's look at our product formula from the last video. Because of the trivial action, we know that the cardinality of H0 G sub Q Z mod P to the NZ is just the cardinality of Z mod P to the NZ, which is P to the N, because everything here is fixed under the trivial action. Since P is odd, H0 G sub Q mu sub P to the N is trivial. We talked about that many videos ago at the beginning of chapter 4. And then in the product, the terms with L not in S are 1. That's easy to check based on what we've discussed. If L is in S and not infinity, the associated factor in the product formula is just, by definition, the size of H1 of G sub L Z mod P to the NZ over the size of H0 G sub L Z mod P to the NZ. But by proposition 3, that's just the size of H0 G sub L mu sub P to the N times L to the P-adic valuation of P to the nth power. Okay, and then it's a standard fact from algebraic number theory that the number of P to the nth roots in Q sub L is the GCD of L minus 1 and P to the N. So see like Gouvea's book on P-adic numbers, for example. And so this is the order of this guy. This is this order here. It's the order of H0 G sub L mu sub P to the N. Since the size of Hom G sub R Z mod P to the NZ is just 1 from like basic group theory, if you like, the factor at L infinity in the product is just 1 over P to the N. And so putting all of this together and applying our product formula, we find the following. The size of H1 sub cal L G sub Q Z mod P to the NZ is P to the N times the product over primes that are in S but not infinity of the GCDs of L minus 1 and P to the N. Okay, so this is an example of how to use that product formula from last time, which we'll have to use in the proof of Fermat's last theorem as well, but this is an easier example. Okay, so we successfully used the product formula on Galois cohomology from last video. Just a couple of remarks here. The group H1 G sub Q Z mod P to the NZ is just Hom G sub Q Z mod P to the NZ because our action is trivial. And this group, what does it do? It just classifies all cyclic extensions of Q of degree dividing P to the N. So what's the difference between that and H sub 1 sub cal L G sub Q Z mod P to the NZ? Well, the latter just gives us those extensions that are unramified outside S. Okay, so this is all of those extensions. These are the ones unramified outside S. Okay. Another remark I want to make is using the above analysis, you can actually get a proof of the Kronecker-Weber theorem, which says that every abelian extension of Q is contained in a cyclotomic field. I would see Milne's class field theory notes for standard proofs of this theorem, and I would see CSS page 113 for a proof using the above theory and setup. And then finally, I want to talk a little bit about the growth of Selmer groups, because as mentioned way back in chapter 1, we're going to need to know how the size of the Selmer group increases as we enlarge the set of primes at which ramification is allowed. And this proposition deals with that. So proposition 5, let's let P be a prime, and we'll suppose the cardinality of X is a pth power. Let's let cal L be a collection of local conditions. And let's let Q not equal to P be a prime, for which L sub Q is H1 G sub Q mod I sub Q, X to the I sub Q. In other words, we have no ramification at Q. Define a new collection of local conditions, cal L prime, by big L prime sub little l equals big L sub little l if L isn't Q. So it's just whatever it was if L isn't Q. But then at Q, we allow potential ramification. So big L prime sub Q is H1 G sub QX. It's everything. It's the whole H1. Then, again, how is the size of the Selmer group changing as we allow one more ramified prime in? Well, the ratio, the size of H1 sub cal L prime QX to the size of H1 sub cal L QX is no bigger than the size of H0 of G sub Q X star. Okay, so the proof of this can be found in CSS page 113, but this gives you a handle on kind of how much bigger the Selmer groups can be when you add in even one more kind of allowably ramified prime. Okay, so next time we will do some more calculations with this. So I'll see you then. Thanks for watching.